Hello, I am going to start this course on thermodynamics in what might seem to be an unusual place. I am going to start teaching thermodynamics by first reminding you about Newtonian physics. The reason for this is that there are general rules that we use when constructing physical theories, and these general rules are most easily seen in Newtonian physics. I will thus explain how they work for this theory before explaining how they are used within thermodynamics. Ultimately, we will see that we can construct an analogy between the laws of thermodynamics and Newton's laws. In fact, this is pretty much how the theory of thermodynamics was developed in the first instance. Physicists essentially use Newton's main mathematical tool, the calculus, to study the behaviour of engines, materials, and so on. The fact that this worked was quite remarkable, given that the objects under study, essentially lumps of matter or complicated machines, appeared very different to the celestial bodies, frictionless balls, and so on that are the mainstays of Newtonian physics. In fact, the explanation as to why you can use these Newtonian tools to describe matter only came later with the re-emergence of the atomic picture of matter and the development of statistical mechanics. I am getting ahead of myself though, so without further ado, let's begin with Newton's three laws of motion that state a body remains at rest or travelling at a constant speed unless acted upon by an external force. The force acting on a body is equal to the rate of change of the body's momentum, and every action has an equal and opposite reaction. In this video, we are going to consider the first of these laws. A body remains at rest or travelling at a constant speed unless acted upon by an external force. Our focus is not going to be the meaning of this statement, which you should understand, but rather the purpose this law serves in Newton's theories of motion. Thinking about the purpose of this law brings us to a very old philosophical question that the pre-Socratic philosophers in ancient Greek first wrestled with. The problem in question is the nature of change. In other words, the ancient Greek philosophers wanted to understand what change was and why things changed. To a modern ear, these ideas now perhaps feel rather antiquated and strange. After all, the question, what is the nature of change, sounds almost absurdly philosophical and imprecise. As I will hopefully convince you, though, the thinking of people like Zeno, who pointed out that supposing that there is any change or multiplicity leads to contradictions, was actually surprisingly astute. In fact, I think that within this statement there is almost a foreshadowing of ideas that would later appear in quantum mechanics. What I like about the ancient Greeks is that their science mixed both the physical and the metaphysical. People like Pythagoras, for example, believed in a strange bag of things that ranged from his famous theorem to a belief that people should not eat beans. We, modern scientists, believe that we have put aside these early suspicions and that our modern approach contains more rigour and is thus more precise. The truth of the matter, however, is that there are many things at the very core of modern science which are assumed and not rigorously justified. For example, we have no proof that the laws of the universe are written in mathematics. In fact, we have nothing other than anecdotal evidence that conclusively proves that the universe will continue to behave in the same way in the future as it has behaved in the past. Bertrand Russell made this point rather pithily when he pointed out that the man who has fed the chicken every day throughout its life at last wrings its neck instead, showing that more refined views as to the uniformity of nature would have been useful to the chicken. We thus really have no evidence that the universe has any fixed and immutable laws. For the ancient Greeks, and even more so for post-Enlightenment scientists such as Newton and Faraday, their belief in nature's immutable laws was intimately connected with their deeply held religious faith in the existence of a benign deity. In other words, for Newton and Faraday, the fact that there appear to be laws of nature proves that God exists. I personally am an agnostic, but largely because I find the atheists that argue that the non-existence of God can be proved by science deeply irritating. To me, science cannot possibly prove anything about the existence/non-existence of God, because at heart, much of its logic is circular. As an example, in this course, we will introduce the laws of thermodynamics, which tell us that total energy is conserved and entropy must increase. We then develop a mathematical theory based on these two laws that explains why many phenomena occur the way that they do. In my view, this in no way proves the first and second laws of thermodynamics. After all, the essential argument runs as follows. The laws of thermodynamics tell me that I cannot build a perpetual motion machine. I have never encountered a perpetual motion machine, therefore the laws of thermodynamics must hold. The argument here is clearly circular. Having said that, it is still useful to learn thermodynamics because this theory allows us to rationalize the many observations we have made of the universe thus far in terms of two simple rules. In other words, these rules serve as a mnemonic device that allow us to remember many things about the universe. Having taken these philosophical considerations to heart, let's look again at the ancient Greeks' question on the nature of change and imagine how Newton might have answered it. Although he never stated as much in his lifetime, I like to think that he would have started something like this. To understand change, we must first precisely define it by explaining the absence of change. This is what I believe the first law accomplishes. Remember that the first law states that a body remains at rest or travelling at a constant speed unless acted upon by an external force. This statement begins with a noun, a body, that tells us what part of the universe the law is concerned with. In science, we frequently use the expression the system to refer to a part of the universe that we believe is particularly interesting. In Newton's first law, the system is a body, which is a word we can use to refer to a ball, an arrow, a car, or even a planet. The next key word in this statement is the word external, and in particular the concept of an external force. Newton uses the word external force to refer to pushes and pulls on the system, in this case a body, that are applied by something that is external to it. That is to say, these pushes and pulls are not being applied by the body. Given this, the rest of Newton's first law, can be seen as an answer to the following question. How does the system behave when it is on its own, unaffected by anything? The answer Newton comes up with is that the system, a body, will remain at rest or continue to travel at a constant speed if no external force is applied to it. Thinking back to our initial question on change, Newton thus defines change as something that happens to a system when it responds to an external stimulus. If a body is pulled by an external force, it will speed up. If no such force acts, its velocity will not change. In physics, we call any behavior that the system will persist with unless acted upon by some external stimulus, a state of the system. In Newtonian physics, the velocity or momentum, which is just the velocity multiplied by the mass, thus defines the state of the system. It was this idea that the momentum of the system defined its state that made Newton's ideas truly radical. Prior to Newton, it was assumed that a system's position in space defined its state. This was the main idea of Aristotle, who might have argued something akin to a body remains at rest unless acted upon by an external force. We can instantly think of problematic cases for this law of nature, however. For example, consider an archer firing an arrow from his bow. Once the arrow leaves his string, no external force acts upon this system, the arrow, and yet it continues in its motion rather than coming to rest because of the absence of the external force required by Aristotle. This was a major scientific conundrum in its day, and thinkers such as Descartes, of Cartesian coordinates and I think therefore I am fame, had developed elaborate theories involving vortices that form in the air around the arrow and that suck it along its path. These theories are in the mainstream no longer, however, because they were conceptually complex and difficult to understand. When compared with this incomprehensible figure from Descartes' notes on his vortex theory, Newton's notion that the body will continue along its present course at a constant velocity unless an external force acts upon it seems rather beautifully straightforward. Newton thus revolutionized physics by generating a new answer to the question, how does the system behave when it's on its own, unaffected by anything? This question is important because within physics, a system changes because something external to it perturbs it. We explain these changes by noting that the system's state changes when it is stimulated by some external entity. Our answer to the Greeks' question on change is hence that change to a system is anything caused by an external stimulus. To be clear, Newton did not develop this way of thinking about change. What he did was to change the prevailing view on how the state of the system should be defined. We thus moved from defining the state of the system in terms of its position in space to defining the state of the system in terms of the system's momentum. This rethinking of the definition of a state has been common in all the major paradigm shifts in the history of physics. For Newton, the state of the system is given by its momentum. Within classical thermodynamics, by contrast, the state of the system can be defined using a set of extensive thermodynamic variables. This becomes more complicated in statistical thermodynamics when the state of the system is given by a probability distribution function, and even more difficult in quantum mechanics where the state of the system is given by the wave function. I believe, although I acknowledge that I'm not an expert and that I may well be wrong, that one reason that we have had to increase the complexity of our theories in this way is connected to a fundamental problem in the way that we do science. What is more, this neatly brings us back to the quote from Zeno when he stated that supposing that there is any change or multiplicity leads to contradictions. Remember that physics is predicated on the definition that systems change when they are acted upon by an external perturbation. So as an example, this box, the system, moves because it is pushed by this red bird, which is part of the external world. The problem, however, is that we must do something to the system to observe it. We thus cannot really ever observe how a system behaves when it is on its own, unaffected by anything. Given this, I would thus ask, how can we ever know how to define the state of the system? Given that the state of the system is a behavior the system will persist in if it is not acted upon by an external stimulus. These rather deep philosophical questions aside, let's finish by summarizing the key points from this video. Physics is our attempt to answer an ancient question on the nature of change. In physics, we state that change happens when something external to the system acts upon it. Our first step in developing any physical theory is thus to characterize the way the system behaves in the absence of an external agent. In Newtonian physics, this is done by asserting that a body remains at rest or travelling at a constant speed unless it is acted upon by an external force. Thank you for your attention.